Hi everyone, I hope you're doing well. I had a few students ask me about question 26 on work session 16. So this question asks us to calculate the pH of a 0.050 molar sulfuric acid solution. So just the first thing we need to recognize here is, what are we working with? What's in my beaker? Well, we know that sulfuric acid is a strong acid, right? However, it's not just a strong acid, it is a diprotic acid, which means it has the ability to donate 2 protons, right? Because we understand that a Bronsted acid is a proton donor. And in my online lectures, I went over the topic of polyprotic acids, and I mentioned that generally the formation of the hydronium ion, the first step, inhibits the formation of additional hydronium ions in the second step. So usually we just calculate the pH of most polyprotic acids as if the first step were the only step. However, in dilute sulfuric acid, like 0.050 molar, that's not the case. And it's because the second ionization step is actually has a relatively large equilibrium constant compared to other weak acids. And so I worked an example in my online lecture, calculating the pH of a 0.05 molar sulfuric acid solution. And so I'm going to do the same thing here for question 26. We are calculating for a 0.05 molar solution. So first things first, anytime you're doing these problems, you have to write down the reaction, like what's taking place, right? And so when we're looking at sulfuric acid, H2SO4, we have identified that as a strong acid. And so I always encourage students to use the definitions to help guide you, so you're not memorizing how to predict the products, but you can derive them. So an acid is a proton donor when we're talking about the Bronsted definition, and a base is a proton acceptor based on the Bronsted definition. Good. And so when we're working with sulfuric acid, in the presence of water, water is acting as a base. Remember, water is amphoteric and it can act as an acid or a base. It depends what you're mixing it with or what it's in company with there. That first ionization step, we're going to witness complete dissociation. So that's why the arrow is just pointing towards the right. And we're only donating 1 proton at a time. So the conjugate base of sulfuric acid, because it's a proton donor, would have 1 less hydrogen. So instead of H2SO4, what would the conjugate base look like? Excellent, HSO4. And then it went from neutral, originally sulfuric acid's neutral in charge. We're losing a positive charge, so what should be the charge on the conjugate base here? Okay, it should be negative. Excellent. And because water is acting as the base, it's a proton acceptor. So you go from H2O to what? To H3O, and you're gaining that positive charge. So this is H3O plus, and we recognize that as the hydronium ion. Hydronium ion is the conjugate acid of water. Okay, good. So we have complete dissociation. And because of that, the concentration of sulfuric acid, when it completely dissociates, is actually equal to the concentration of the products, because we completely make the products and they're all the same. So as the dissociation occurs and everything's 1 to 1 to 1, these concentrations end up being equal. And so in this case here, for this problem, we said it was a 0.050 molar solution. And so that's the concentration of hydronium ions that are being produced. And we're going to use that later on to figure out the pH, because the pH is the negative log of the hydronium ion concentration. So this information will be very helpful for us later on. All right, and actually, pretty much in the next step here. Remember, since it's a dilute sulfuric acid solution, we do need to take into account the second ionization step. So Now HSO4 minus is going to behave as an acid again because it's going to donate that proton. But is this designated as a strong or as a weak acid? Yeah, it's not part of the list of strong acids, so therefore we can assume it is weak. And when it loses a proton, what is its conjugate base? It's not HSO4 anymore, it's lost a hydrogen, so it's SO4, and then what's the charge? 2 minus, because you've lost a positive charge there, right? A positive proton. And you recognize that sulfate is just one of those polyatomic ions we've learned since first semester general chemistry, right? Alright, and because the hydrogen sulfate lost a proton, water's acting as a base, we create the conjugate acid of water, which is the hydronium ion. So, our goal is to figure out the pH. And so, we need to look at how much hydronium ions are in solution. We have to take into account both sources of hydronium ions, one from the first ionization step, which will be significant. We have 0.05 molar, but we're going to get some as well from the second ionization step. And because we're working with a weak acid, we need to use a Rice table. Remember, our Rice tables are only used for weak acids or weak bases, right? We're not using it for strong acids or strong bases because there's complete dissociation. All right, so from this first step here, we see that the concentration of HSO4 minus is 0.050 molar, and the concentration initially of hydronium ion is also 0.050 molar. So let's go ahead and write that in here into our table. I standing for initial. We didn't have any sulfate at the beginning initially. And then over time, this is minus X, and then sulfates plus X, and then plus X based on the stoichiometry. And then at equilibrium, 0.050 minus X, X, and then 0.050 plus X here. All right, we're working with a weak acid, so do we need the Ka or Kb? We need the Ka, right? And this is something you would look up in the literature, or it would be provided on an assessment for you if you're taking my class. So we have the Ka, and a lot of times in literature it might be represented as Ka2. You look it up for sulfuric acid, and then you see Ka2, 2 meaning the second ionization step. But this is products over reactants. And so you plug in everything at equilibrium. We're talking about the equilibrium constant, so you plug in everything at equilibrium. And you set that equal to 0.012, which is the Ka2 value. All right, so in this case here, X is not going to be small enough to ignore. So we will have to do the quadratic formula eventually. And that's just because the concentration initially is not significantly greater than the Ka value. This number, the initial concentration, should be about 1,000 times greater, such that the change in X is insignificant. But because Ka2 is pretty large relative, then the change in X will be significant in comparison to the 0.05. Okay, so we'll have to do a little math. I'm going to simplify and try to get us into the ax squared plus bx plus c is equal to 0 quadratic formula. So I got 0.050x plus x squared over 0.050 minus x is equal to 0.012. And then to continue on to simplify, 0.050 x plus x squared is equal to 6 times 10 to the negative 4th minus 0.012x. And then x squared plus 0.062x minus 0.0006 is equal to 0. And then have to plug that into the quadratic, so x is equal to negative 0.062, and that's the b, so negative b, plus or minus the square root of b squared. And so put the parentheses 0.062 squared minus 4ac, so 4 times 1 times c, which is negative 0.0006, over 2 times 1, 2 times a. And when I plug that in, I got two different values for x. X is equal to negative 0.0705. I like to keep all my digits so there's no rounding error. Or x is equal to 0.0085095. Right? How do you choose which is the solution for x? Well, at equilibrium or any time, we can never have a negative concentration. So if x was negative 0.07 and we look at our table, that would imply that the sulfate concentration at equilibrium is negative. That's not going to happen, right? So the only solution that makes sense here is x is equal to 0.0085095. Now coming back to what we want to find the pH. And so a lot of times I'll tell my students, write down the formula because it kind of helps guide you. So pH is equal to negative log of the hydronium ion concentration. So, and the hydronium ion concentration at equilibrium, right? And so what we really want to look at here is what will this number be? The 0.05 plus x will give us the final concentration of hydronium ions at equilibrium after both dissociations have occurred to their extent, okay? And so, in this case here, the hydronium ion concentration at equilibrium is equal to 0.050 plus the 0.008595. And so, therefore, the hydronium ion concentration is 0.0585 molar. I'm going to plug that number into the negative log of the hydronium ion concentration, and there you would get a pH of 1.23. Alright, so you get a pH of 1.23. I'm always a big believer in making sure that the solution you get from working through a word problem matches the theory, right, and your expectations of what should happen in your beaker. So in our beaker, we recognize we have a strong acid, sulfuric acid. It's dilute, but still it's a strong acid. And so even before doing all this work and Rice table and math, we should predict that the solution would be acidic. And on the pH scale, that means it should be less than 7. The fact that after we've done these calculations, we got a pH of 1.23 matches our intuition that it should be a pretty acidic solution. All right, I hope that clarifies this question for you. If you have any questions, don't hesitate to contact me or send me an email. Take care.